In the previous video, we learned that y is equal to 10 to the x and y is equal to log of x are inverses of each other. Logs are inverses of exponential functions, right? And one thing I didn't mention in my previous video that I really wish I was able to do was show you what goes around comes around. For example, I got 10. If I plug in 2, so 10 squared to the exponent, I get 100. Now you'll see here, if I do log of 100, I better get 2, and which I do. So you'll see, let me just write in this corner. If I plug in 2 for the exponent, I get 100, and if I do log of 100, I get 2. What goes around comes around, which again tells us they're inverses of each other. They kind of undo each other. Inputs and outputs are switched. All right. It's kind of a point I wanted to make in the last video. Whoa, all right, let's begin. How do we solve the problem that I proposed earlier? Let's say 20 is equal to 10 to the x. All right, well, one thing to keep in mind is this 10 right here is what's considered our base. All right, and this is what I would plug in, right? Just before I told you 10 squared, I would plug the 2 in for the exponent. This is my input. And the number on the outside is considered my output. What I plug in, I want to get this 20. This is my output. So what I want to figure out is 10 raised to what power gives me 20. All right. The other video is 25. We'll stick with 20 here. Well, we can use the fact that this is the inverse of 10 to the x, right? There's like an invisible 10 there. So what do I do? Well, when we're converting from exponential to logarithm, we start off, we write log, and we're going to put our base down below here. This tells us that this log means inverse. This is the inverse of 10 to the x. And let me just put parentheses is equal to blank. Okay, well, let me first just write a few things. What goes inside our log function is our input. And obviously, whatever we plug in, this is going to be my output. Okay, well, remember, when you're inverses, what do? You switch the x and y. You switch your inputs and outputs. So that is what we're going to do. You see, this is my input. So that has to now become, has to become my output. And this is my output, which now has to become my input. Okay, and that's it. That's how we convert from exponential to logarithm. We're going to continue to get practice. I know it's a little bit hard right now. Okay, well, let's solve this. All right, let's use our calculator here. Okay, and luckily, since we're using 10 to the x, we can use this log. Let's type in log of 20. And we get 1.301. So 1.301. This is my answer. Well, that means if I plug this back into my function, I should get 20. If I do 10 raised to the 1.0301, I better get approximately 20, maybe 19.99 or something like that, right? So if I do that, let's do 10 raised. So I do 10 raised. Now, I'm not... if I type the entire thing, I'll get 20, and I'll go ahead and do that. So 10 raised to the, let's just start off with the estimate. It should be 301. Let me fix that. 1.301. So this is 10 raised to the 1.301. I should get approximately 20. Good catch there. 1.301, and I'll just put a few more. 02 9996. And look, if I put the entire thing, look at that, 20.000002. All right, so I get pretty darn close to 20. I'm able to solve a problem I wasn't able to do beforehand. All right, well, let's go ahead and start off maybe with a different problem. Let's see here. Let's say I got, I want to figure out 2 raised to what power is 16. All right, this time we'll use something that doesn't have a base 10. Now we can actually solve this, right? 2 raised to what power is 16? Well, if we look over here, because it's even, I think we'll be able to make this work in multiples of 2. So let's say if you multiply 2 out 6 times, 2 to the 6, that's 64. That won't work. Let's try 4, 2 raised to the 4. 16. So that tells me that my answer better be x equals 4, right? So we know the answer before we get started, but let's verify it using logs. Well, again, let me just label some things. The 2 is my base. The x is what I would plug in, that is my input, and the 16 is my output. So let's convert this to logarithmic form. So let me write log. Well, the base is going to go right there. This is going to notify to me that this is the inverse of 2 to the x. Let me put a set of parentheses here is equal to blank. All right, well, again, what goes inside my log function inside here is considered my input, and what we put on the outside is now going to consider my output, right? And again, the 2's match, which tells me that they're going to be inverses of each other. Well, your output has to become your input, so that tells me the 16 goes here because they're inverses. The x, the input, has to become your output, so that's going to go there. All right, now this is a problem because I can't just go to the calculator and type log of 16, right? Because my calculator right now that you see here, if you look, it doesn't have a 2 there. Remember, if it doesn't show it, it's an invisible 10. That's a problem, 1.204. See, that's not gonna work. Okay, well, there's a little trick. And the trick is called the change of base formula. In other words, this is what we can do. If we do x is equal to, and we do log of 16, okay, divided by, okay, log of 2. All right, this is just a little trick. This is actually called the change of base formula. I won't really go too much in depth in this videos about it, but pretty much if you do log of 16, log of your input divided by log of base, this is, you always have to keep it in this order. Just remember that the log base should always go on the bottom. We are going to get our answer, which is, let's type it in. So the little trick, log of 16 divided by log of 2. And if you look at that, exactly what we got, we get 4. All right, cool. Let's go ahead and solve another problem, maybe one that's a little more challenging. So let's go ahead and do, let's say 42 is equal to 3 times, no, I don't want to use 10. Let's say 6 to the 2x. All right. Let's complicate this problem up a little bit. Well, this is a problem because here I have my base, which is 6. This is my base. This 2x is my input. Remember, it stays the same. This, even though before it was x, now it's 2x is my input. The 42 is my output. But then we have this 3 that's just sitting there. And so how do we label it? The dilation or the stretch factor, vertical stretch, etc. What are we going to exactly do with this 3? Well, it's kind of hard to work with. So the best thing to do is let's just get rid of it. So let's divide 3 to both sides and actually just get rid of it. So let's go to my calculator and let's do 42 divided by 3. And when I do that, I get 14. So I'm going to get 14 is equal to 6 to the 2x. All right. Now that I just have my output, my base, and my input, now we can turn this into logarithmic form and solve for it. All right, so let's convert it to logarithmic form. We're going to get log base 6, and I'll put a set of parentheses equals blank. Well, this is my output, so that now is going to become my input. And this is my input, so that's going to become my output. All right, so far we got log base 6 of 14 is equal to 2 to the x. Well, to solve this problem, let's use our change of base formula. Let's use that on this. Let's type log of 14 divided by log of 6. And let's figure out what that answer is right there. So we do log of 14 divided by log of 6. And we're going to get 1.4728. So we get 1.4728 is equal to 2x. Now I can divide the 2 to both sides and we're going to get our final result. So x is equal to, and let's go ahead and do that again with the calculator. Let's say divided by 2, and that gives me 0.7364. All right, I'll write all those out. 0.7634. This is my answer. So that means if I plug this in all into this function, I better get 42. So let's do 3 times 6 raised to the 2 times 0.7634. And let's see if we get approximately 42. All right, so let's go ahead and do that right over here. 3 times 6 raised, and I'll just put a set of parentheses, 2 times 0.73644, and we better get close to 42, right? 41.999. You see, a problem that's so complicated to solve, 41.999, we're getting pretty close to 42. A problem that was so hard to solve earlier. And now we are doing these complex problems where we have an input that's 2x and a vertical stretch times 3, and we're able to still solve this equation as long as we do a few simplification stuff, and then we go ahead and just solve for it, all right? So maybe we should go over one more example problem that I like to go over, which is, let's say I want you to solve 10 to the x is equal to 0. 10 raised to what power is 0? Well, first of all, let's acknowledge, right? 10 squared is equal to 10 times 10, which is 100. When you have a positive exponent, that means you multiply your base by the number of times on the exponents, right? 10 squared was 10 times 10. Well, what about 10 to the 0? Well, 10 to the 0 is 1. Okay, because 10 divided by 10 is 1. See, when it's positive, that means multiply. When it's 0, that means we start to divide. So we divide 10 by itself. 10 divided by 10 is 1. Okay, well, what about 10 to the negative 1? Well, that means now, for 10 to the 0 was 1, right? And so we have 1. Well, the negative exponents means divide. So that means now we're going to divide from the previous exponent. We're going to divide by 10, which is just 1 over 10. Therefore, if we did 10 to the negative 2, that means divide again. So we would just get 1 over 10 squared, which is 1 over 100. So you'll see there's no way to raise 10 to some power to give me 0. And this is why this problem is not possible. If we do log, okay, because it's 10, we know there's like an invisible 10 here. You can put it, you don't have to. Let's do equals blank. Okay, this is your output. So that's now going to become your input. And this is your input that has to become your output. And watch, if I try typing this into my calculator, I better get error because this is not possible. So log of 0. If we do that, look, we get error domain because it's not possible. We can't do that. There's nothing we can raise 10 by to get 0. All right. Hopefully those 3 examples helped you out to understand how to convert from exponential to logarithm and how they're useful to actually solve problems that we wouldn't have been able to do a long time ago.